Question 11, the last one, nearly at the end. Find dy by dx in terms of t. We did all right with this first part. Those who tried it, we know that in parametric equations, to get dy by dx, we need dx by dt and dy by dt. So x is 2 plus t to the minus a half. Y is t cubed minus 3t. So dx by dt is minus a half, 2 plus t to the minus 3 over 2. And dy by dt is 3t squared minus 3. You've got marks. There we go, 2 marks straight away for getting those two first derivatives. Dy by dx, therefore, and the third mark was just for dividing these. No simplification needed. 3t squared minus 3 over minus a half, 2 plus t to the minus 3 over 2. I know, that's horrible, but that got you all the marks. You didn't have to do anything with this negative power down here and this minus a half hanging around down there. You can dislike it if you like, but that's the 3 marks.
That's all you
Good.
have to do.
That's it. Yep, 3 marks. Part 2. Now this one, this caused quite a kerfuffle in the maths office last summer. Find the coordinates of the stationary point on the curve and determine its nature. I'm going to do something here that is that. It is only 4 marks for doing this. And the first part of it is find the coordinates of the stationary point. That has got to be 2 marks. So determining its nature must be at most 2 marks. Let's think about that in a moment. Right, part 2 then. What we need to do first, at a stationary point, dy by dx equals 0. If dy by dx equals 0, that leaves us with, this isn't going in, there we are, that leaves us with 3t squared minus 3 over minus a half, 2 plus t to the minus 3 over 2 being equal to 0. Now, actually there's a couple of ways of approaching this. There's a couple of things that could happen. This could be 0. It's tempting just to say this could be 0 if the top line is 0. It turns out to be true, but actually there's a little bit of, you have to be slightly careful with that. Because this, although it's on the bottom of this fraction, it's kind of also really on the top, because it's a negative power. So really, the thing that we're wanting to be true is minus 2 lots of 3t squared minus 3 times 2 plus t to the 3 over 2. That's the thing. Now they let you get away with just ignoring that because it was on the bottom, but really perhaps they shouldn't have done. This gives us, I think, 3 solutions. This gives us t equals plus or minus 1 and t equals minus 2 as the 3 solutions. They're the 3 values for which that would be 0. But if we zoink up here, we see that t is between minus 2 and 0. So because t is between minus 2 and 0, and not equal to minus 2, actually, there's only one value that comes out of that. T equals minus 1 only. That's the only solution. Minus 2 is outside the range of values of t, so is plus 1. So t equals minus 1 is the only solution. The question said, find the coordinates of the stationary point. So having got t equals minus 1, we have to sub them back in to the x and y values. If t equals minus 1, x is 1 over the square root of 2 minus 1. That's 1. Y equals minus 1 cubed minus 3 times minus 1. That's minus 1 plus 3. That's 2. So the point is the point 1, 2. Are we happy with that? I've lost all of my working out, but I think that's fine, isn't it? I've got bits of paper all over the place now. Yes. Cool. Got it. Right. Then it said, and determine its nature. And this is the bit that caused a little bit of an argument with this. Now, the first thing that I want to say, and for those who are interested, I'll talk about this more later, but when you're dealing with parametric equations, d2y by dx squared is not equal to d2y by dt squared over d2x by dt squared. Okay? That's the first thing to say. That simply isn't true. The second derivative of parametric equations is a somewhat more complicated formula that involves basically having to use the quotient rule. The fault with this is that we are differentiating our first derivative with respect to x, but to get each of these we're differentiating our first derivative with respect to t, not differentiating with respect to x. So you have to use the chain rule to allow you to differentiate it with t whilst differentiating with respect to x. That's the first thing to say. So if anybody tried to differentiate these things again and then divide them, no more marks. You're just going in the wrong direction with it. And actually it gave you the wrong answer anyway. It gave you the wrong kind of stationary point. It wasn't about differentiating. Now, you can get there by differentiating. It's a lot of work, and I will show you how to do it, but not right now. You don't need to know how to do it. You're not expected to know how to do it. We do have another way of determining the nature of stationary points. What's the other way of finding out nature of stationary points? Going right back to early days of core 1. Go on, Joe.
Finding the gradient just before or after the point.
Exactly that. Finding the gradient either side of the point. So that's our only option. You can do this in a number of different ways. I did it on a different bit of paper. I did it by saying if t equals, we're going to do the left and right method. So if t equals minus 1.1, x is 1.05, and that gives me dy by dx is minus 1.08, which is negative. If t equals minus 0.9, so this is, I've got either side of my minus 1 here, x is 0.95, so I've got either side of the x value in doing that. Dy by dx, in that case, is 1.32, that's greater than 0. Can you see what's happened here? We've gone from this being negative, when x is... hang on, we've gone from this being... I've just written that the wrong way around, have I? When x is 0.95, the gradient is positive, that's a positive line, there we go. When x is 0, the gradient is... When x is 1, sorry, the gradient is 0. Oh. And when x is 1.05, the gradient was negative. That looks to me like it's a maximum. So the nature of the stationary point was that it was a maximum. That was really harsh, that, because so many people launched into the second derivative. It made me think last summer. I was quite pleased with myself that I thought, hang on, you can't just differentiate them again and divide. That doesn't work. And so I went straight into doing it that way. We've got time to finish it off, but it's not quite end of lesson yet. Part 3 said, state the range of values of x and the range of values of y. So what's going on with that? T, remember, t is between minus 2 and 0. So think about what happens to 1 over the square root of 2 plus t. If t is minus 2, then as t approaches minus 2, that approaches 0 on the bottom, so that it becomes infinite, doesn't it? As t approaches 0, that approaches root 2 on the bottom. So we're going from something infinite to 1 over root 2. So I think x is greater than or equal to 1 over root 2. And that was 1 mark. Y is t cubed minus 3t. Again, let's think about this. If t is approaching minus 2, as t approaches minus 2, that gives me 8. What does that give me? Minus 8 plus 6, so that gives me minus 2. So y is not equal to minus 2. We did find a maximum value on this curve, and it was the only stationary point. And the maximum value came when y was 2. So its maximum value must be 2. That was the only stationary point, remember. So having reached 2, it's never going to go higher than 2. So that's the boundaries for that. And really quick with this one. I don't think many people even attempted this. At the end of all of that, think what we've got. We know that x starts at 1 over root 2. 1 over root 2 is less than 1. We then get a maximum point at the point 1, 2. And we then get a curve that, as it heads in this direction, is getting closer and closer to minus 2. So I think we've got a curve that is doing that. We need to mark the asymptote down there at minus 2. That's the point 2. That's the point 1, 2. That's the point 1 over root 2. That's x. That's y. Again, they only gave you 1 mark for that at the end, which they've obviously run out of marks at the end of this, because that's quite a lot of work, isn't it? But there we go. And that is maths.